ladies and gentlemen, John Adams from Twitter.
Hey, check. Oh, hi, okay. I think I'm on here. There we go. Okay, so I work in the operations department at Twitter. We're a pretty small team. We're around 8 people, and what we do is we concentrate mainly on software performance, availability, capacity planning, and configuration management. We don't deal with the actual physical plant of Twitter. We don't install servers. We don't rack anything. We actually use managed services. And we're currently going through NTT America. They've been really good to us as far as delivering servers on time, being able to grow our infrastructure very, very rapidly, and handle most of the problems with the network side and sort of load balancer and things like that. We still have a lot of control over our network, but the majority of the hard problems are solved by NTT. We don't use clouds. We really want raw processing, and we want to be able to look at the metrics of a system and accurately predict what's going to happen. There's a place for clouds. I'm sure they work for a lot of people, but given the scale that we're under and the amount of traffic that we process, it's currently not working. I mean, there's maybe some chance of using repeatability and being able to take a system, create a template of that system, and reproduce it many times. But at the moment, it's not really working for us. And we'd rather spend our time working on the real hard computer science problems that we're under. Now, in the last year, we had 752% growth. And that was in 2008, we had 752% growth. You would think that's a lot of traffic because we moved from about 500,000 users to somewhere around 5 million. Well, that was only the beginning. If you look at that chart, the previous graph that I just showed you is a small block right there in that beginning. The first major uptick in the graph is in November. That would be the election. And that second major kind of bump and then, dead cat bounce is the uptick from Oprah. Traffic rank trend, we're now in the top 100 sites. And our uniques, they just keep going up and up and up. We're at about, it looks like about 26 million compete-wise. I'm not going to give you the real numbers because I can't. But a lot of reports are coming out saying that the growth is slowing. Well, they're not. It's just not slowing down. It's really hard for an outsider to measure the actual traffic of Twitter because we receive a lot of traffic from both API and SMS. And all of that traffic has led to just an insane amount of pain. It's also given us a real high level of appreciation for institutionalized fear. And by that I mean, when we're about to make a change, we panic. It's a controlled panic, but we worry intensely what's going to happen to the site and what the user experience is going to be. So, what do? Well, we had to come up with a mantra, a way of correcting all the problems that we've had in the system. And the way that we do this right now is we find the weakest point in the infrastructure, and we do this through metrics. We have logging, intense logging, science, and deep analysis of the data that's coming to us. We then take corrective action based upon those metrics, and we have built a process around using the metrics to make decisions. And we also want to have a level of repeatability in the data. We want to make sure that the data that we're reading is relevant to what's happening to the system, that we understand that each of those metrics means something, that they're actionable, we have some work we can do, and that when we collect those metrics, we collect them in a consistent way. So let's go into a little detail on that. As far as the way that we find the weakest point in our infrastructure, we collect metrics and we make a lot of graphs. And I'll show you in a couple minutes a little dashboard that we have. To us, the individual metrics that we collect on the site are completely irrelevant. If we look at a single metric on a single server, it tells us nothing. We're more interested in looking at the entire request pipeline. We want to understand that the web server has an interaction with the database, which has an interaction with the queues, which then makes something happen or increases or decreases latency. We use science. We use real graphs, charting, predictions, and we work that out to find the actual metrics. So you really want to instrument everything you have. It works for Twitter. It'll work on your site. If you have a chance to collect a data point and you can collect it on a relatively quick interval, do that. The best thing you can do is have more information about your infrastructure. At some point, what's going to happen is that you may collect so many metrics that you'll actually hurt the system. In the case of MySQL, which is a great example, MySQL has global table locks. If you keep collecting statistics all the time, you'll actually cause MySQL to slow down. So that's completely unacceptable. Same thing goes for Memcache. Memcache has a global stats lock, which will cause Memcache to slow down. So for most of you, you already have the tools available to do this. You can go out, you can install RD, MRTG, Ganglia. You can easily write custom geometric scripts. You can collect data on relatively rapid intervals. We collect most of our metrics on a 10-second interval. You can probably do it on a 60-second or 5-minute, depending upon the velocity of change that you're interested in monitoring. We then take the data that we've collected and we assemble into this big dashboard. And everyone in the company has access to the dashboard. It has probably, let's say, 1,200 metrics on it. We have a criticals view of the main important metrics that we're interested in. We also aggregate data from places like NTT, like we'll grab XML feeds of the current load balancer statistics. We'll look at Google Analytics. Now, we do a really interesting trick with Google Analytics. We actually put Google Analytics on the whale page, and we put it on our robots page. So instead of looking at the success of the site and how many people are actually staying on the site, we're using Google Analytics to actually collect error. So it's not just for 200s anymore. Once you have all this data, you want to analyze it. You actually need to turn this data into some type of actual information. We do a lot of monitoring around deploys. We want to know where our code base is going. We want to understand, did we make something worse with a deploy? Did the developer make things worse? And we want to understand what the impact is to the customer. And all of this is to create an environment of capacity planning, not firefighting. We don't want to break things. And I think in the beginning, what happened is we had a lot of cowboy stuff going on, a lot of changes happening without control. And we've gotten a real handle on that. Most recently, you may have heard of the Twipocalypse. So the status ID that we use to represent a tweet hit the upper bound of signed integers, so 2 to the power 31. And the bottom red line there represents where that happens. Now, we took all the data and we apply it into a model. Now, I use Mathematica for this because I like Mathematica. You can use R, FitYK, CurveFit, any of these applications. But what we've done is we've predicted the next occurrence of the Twipocalypse. So if you're using an unsigned integer to hold the status ID, guess what? Somewhere around week 25, you're going to be in trouble. So that works out to be October 30th or so. Now, this model might be wrong. I don't know, R squared on this is about 0.99, so pretty close. But we're currently using big ints internally, so our top status ID is like 18 quadrillion. So I don't think we're going to get there anytime soon. I'll probably be dead beforehand, but, Okay. So just quick, brief thing about deploys. I kind of stole this from John Allspaw from Flickr. It's an awesome idea. We modified Ganglia to display the time of the last deploy. So we have 3 different sections. We have Surmise, which is like the indexing pipeline. Then we have Search. And then we have the Twitter Actual. And we graph the time of the last deploy. We can put that graph right next to the current CPU and latency of the site. So you can go back and say, hey, this guy released some code, and at this point in time, our latency went to the moon. What did he do? And we'll display that data at the bottom of our Ganglia graphs, which is really useful. All right, so little fun thing I'm monitoring here. We wrote this script called Whale Watcher. And it was a really simple cell script, but absolutely massive win. Twitter, a whale is a 503. It's basically the back end is timed out. A robot is a 500. It means we've had a real hard server error on the back end, so we probably made a mistake. We go back, we look at the last 100,000 lines of the aggregated daemon and web logs. Now, you can do this with Watch, or you can have it send email. We actually do both. I'll run a window all day that just has this thing running in it. And if the whales per second exceeds our whale threshold, then there's whales. We have to go kill them. So call in the ops team. We take action. So how do we take action against these problems? Well, pretty popular thing to do in the Web 2.0 environment. We have feature dark moding. We call it dark moding. Some people call it levers we can pull. It's switches we throw. What we do is we disable specific parts of the site. We might take away search. We might limit name search. We might disable our interactions with Bitly or third-party URL shorteners. Anytime someone pulls one of those levers, mail goes out to product teams, internal teams. We make sure that everyone's on the same page. We have some features we can throw into a static and read-only mode, but not as much. These things kind of interact with our main configuration management system. Now, if you haven't done configuration management yet, do it now. We started like a couple months into Twitter. Do this as soon as possible. And yesterday, Theo mentioned if you use Puppet, use CF Engine, Chef, it doesn't matter what you use. Get configuration management in place, because eventually you're going to go from 10 servers to 100 to 1,000, and you're going to be lost. There is a problem with configuration management, though, and this is something that we really worked on hard to address. First thing is, it's a really complicated environment. Twitter, in our current configuration, we probably have maybe 100 modules that run all the different aspects of the site. We have multiple administrators. Multiple administrators creates insane unknown interactions. I might update a file, you check it in, we conflict, we merge. It's not like software. Well, maybe it is, but it's not like software in the respect that most of the time the merges are okay. If we have a merge, we might take down 200 web servers, and the only way we know is that the whale watcher starts going off and we start having alarms. And it's our job to go out there and fix the problem in SVN before it gets to all the other servers. So that's just no good. So we brought up we brought up something out of our engineering team with a review process. So we have a second set of eyes on config changes. We use a system called Review Board. It might be familiar to people that do a lot of Ruby development. Review Board is a system where a diff goes into Review Board, and we actually do that diff using a SVN pre-commit hook. The SVN pre-commit hook will cause a failure of any check-in unless it has at the bottom a little message that says, reviewed by John, or reviewed by someone. So if you put that message in like reviewed by nobody, we're going to come after you and yell at you because you're violating the review process. So that commit hook puts the diff on the screen. It sends mail to everyone in the team. And then people in the team can say, well, is this diff okay? Is he going to break anything? Is he conflicting? And if the answer to all those questions is no, then we say, ship it. Go ahead, ship the change. And a SVN post-commit hook then allows that commit to take place. The commit goes in, it goes into configuration management, it goes out to all the servers. So it's a fairly controlled way of making changes. Once in a while, we'll have something slip through where we'll be like, yeah, ship it, it's okay, and then the site goes down. But we try not to do that. And we have a lot of communication. We also use Campfire. It's a 37 signals product. It allows us to put all these requests for reviews, for example, graphs, logs. Everyone can coordinate. We have a history of the chat. We can go back in time. So if the site blew up last night, you can ask people, hey, what happened? What failed? And we have all of this historical data. Plus, we can send graphics back and forth. And that's such a big win for an ops team. You can grab a graph in Ganglia, drop it into the graph. This works really well with Skitch, if you ever use that program. It allows you to take screenshots and then drag them directly into chat and email. So there's a lot of Skitch and Campfire going on back and forth. Okay, so that being said, that's kind of how ops works on the inside. I want to go over some of the subsystems that exist at Twitter and some of the problems we've had and how we've overcome them. Okay, so anyone who's familiar with the request pipeline, you know that there's a lot of limiting factors. Okay, so on the Apache side, you've got your NPM model, how you handle max clients, what the listen queue depth is on TCP. For our search product, we have Varnish. Varnish is a wonderful caching engine. We use that. We have a thread limit in Varnish. On the Rails side, we have a Mongrel limit. Mongrel is the Ruby Rails web server. It's actually written, currently maintained in-house by Evan Weaver. He's one of our engineers. And typically, we will oversubscribe Rails at about 2 to 1. So we've got twice as many Mongrel processes running as we have cores. We have interaction with Memcache. Memcache has a connection limit. MySQL has a connection limit. So at some point in time in the request pipeline, you're going to hit something. So our goal is to reduce these bottlenecks throughout the system. So what we did is we came up with an attack plan. Okay, so for every system that we have, if it's bandwidth, maybe it's a network problem, we are trying to decrease web latency, maybe we add more servers, maybe we add more load balancers. We make decisions based upon the metrics that we've previously collected. From the timeline standpoint, now timeline is the user timeline, the public timeline. These are the ways that people see the site. Our general failure mode has been to delay rather than whale. We hate whaling. We would rather give you a delayed timeline by a couple minutes than give you a blank page. So in that way, we're sort of failing back to what we have statically in our cache when we can't keep DB replication up to date or we can't keep the updates up to date. And I'll get into how that process works in a second. Search is interesting. A lot of database activity on search. It's probably the #1 growth area on Twitter right now. Traffic is pretty high. A lot of database work happening. A lot of work to get the delay out of search and to make sure that the timeline updating is correct and our index pipeline is working. We've had delays in name search and other products, but we're getting better as we add more servers and more bandwidth. Okay, updates, same way. The update daemons process all the updates and all the status updates that come into Twitter. We've done a lot of work on the algorithm, done a lot of work on reducing latency in that respect. From the CPU side, last year we seriously evaluated what we had running, and we switched from AMD processors to Intel Xeon. We picked up about a 30% increase. We also consolidated a lot of our dual core and quad core down to 8 core machines, 30–40% increase there. It saves us a lot of money on data center space, a lot of power. Now, for us, because we're in managed services, we get a nice advantage here where we can do a refresh every quarter. We can update our hardware without too much of a capital expenditure. And it's difficult. If you're buying hardware or leasing and you're stuck in a long-term lease, you can't do this sort of thing. So in this respect, NTT has been a great help. Okay, one sec. Running out here. All right, so yesterday, a lot of Rails bashing. So I understand Ruby's slow. We know Ruby's slow. But Ruby and Rails can be very fast. There are ways around the problem, and you can make this into a pretty useful web platform. So we did a lot of analysis, right? Cache and validation was a big problem for us. And these are problems not so much in Rails. These are problems in Memcache. Active Record is Rails, but it generates bad queries sometimes, and those queries slow down your database. It also increases queue latency, because when the database slows down, the queues can't clear out fast enough. We can't process traffic. Memcache corrupted for us early on in 2008. We had problems in the earlier versions. We've upgraded. A lot of that's been fixed. And again, replication lag is an enemy all the time in this system. We really feel that disk is sort of the new tape now. People looking at SSDs. Most social networks have these O of n squared operations, or O of n by y operations, as you try to traverse the social graph. You try to figure out who's friends with who wants to follow someone. And you're trying to traverse these huge graphs, and you're trying to return a page response in 250 milliseconds. It's really, really hard. A lot of your solutions for this sort of move things in memory, move things somewhere else, pre-cache data. And I think for the most part, Web 2.0 isn't possible without a huge amount of memory. Facebook has a huge Memcache pool. We have a huge Memcache pool. Caching becomes really, really, really important. And you would think in the real-time web, there's not much opportunity for caching, but that's actually not true. We can cache user timelines, which don't update that frequently. We're not really relying on a long TTL. The TTL might be anywhere from 20 to 60 seconds, or in the case of a user timeline, we may only update that timeline when a user makes a new update. So we're keeping all of this state in memory. And we have multiple tiers of caching. And from the operations side, we made a number of changes to improve the performance of Memcache. A typical page creation at Twitter may be anywhere from 100 to 300 Memcache requests. Well, it turns out that when you're setting things in Memcache, the hash algorithm is pretty slow. So we are currently the maintainer, along with a few other people, of libmemcached. Libmemcached is a C interface to Memcache. And we switched over to the FNV hash as opposed to MD5. And we experienced probably 200 or 300% increase in performance, because MD5 is an expensive calculation. FNV is a little faster. We also moved the interaction with Memcache out of Ruby and into native C. So very, very, very fast. You can see here on this graph, 50% decrease in our overall web cluster CPU load when we went to the native C gem. So if you're currently running the Ruby Memcache gem, don't do that anymore. Go get this version, use native. Native is the way to go. Another big thing is our engineer, Nick Collin. He wrote a piece of software called Cache Money. Great name. Cache Money is an Active Record plugin. It provides a read-through and write-through cache against the database. Transparently provides caching. You don't have to remember anymore, oh, did I cache the user object when I made a change? Oh, did I invalidate the user object when I pulled it from the database last time? It's gone. This is completely open source, and you can get your hands on this thing by, I'll have some links at the end you can look at. So that being said, cache everything is not really the best policy, right? You can use that gem, you can enable or disable caching. Invalidating caching is still hard. And when you rely on caching as much as we do, you have this cold cache problem. And the cold cache problem is basically a Memcache server fails. So Memcache isn't perfect, right? If Memcache can go down, you can have random evictions because you've run out of space in Memcache. And you start to experience this when you hit the upper bound of the Memcache pool. We also had data and hash corruption. We managed to find a specific combination of inputs that would cause Memcache to segfault all the time. And once that combination ended up in the user pool, we saw Memcache servers falling over continually until we could fix it. So reliance on Memcache is good most of the time, but be careful. things can happen, and the network memory bus that you have access to is not infinite. You can't keep using the network over and over and over again to write data with no ill effect. Eventually, you'll top that out too. Okay, so we also use web caching. We're using that on the search product. We cache and control abusive clients. We have Varnish sitting in between our search tier. And we also remove some of the cache busting things that happen. If you look at jQuery, it sends out a lot of garbage at the end of every request. Every time it makes an AJAX call or JSON call, it's trying to bust the cache. And we normalize that data on the way in using ESI. And ESI is available in the newest version of Varnish. It's pretty stable. We've been running it on a number of servers without any problems. Really, really big win for us, probably about 40 to 50% cache hit ratio, and we hope to improve that. Okay, let's talk about databases and queues for a second. In general, relational databases are not the end-all, be-all answer to every storage problem you have. Great for users, relational data transactions, bank-style transactions. Really bad if you're polling the database, if you're using queues, if you want to cache data. You don't really need consistency for a lot of the data that we have. A good talk yesterday about key value stores, things like Tokyo Cabinet. There's better ways to store data that's transient than a database. So we use a message queue for all of the communication that happens between daemons on the site. So there's many, many solutions out there. You have RabbitMQ, you have some of the AMQP, I think. At high loads, what we discovered is that the solutions that are currently on the market, once the queue is in durable mode, that is, once you wanted to persist your queue, we had massive performance problems. We actually wrote our own. We wrote a product called Kestrel. And what Kestrel is, Kestrel looks like Memcache from the outside world. You have a set operation and a get operation. These are enqueuing and dequeuing of jobs. Instead of a key value pair, you're storing a queue name and a data, some datum that goes in that queue name. We don't order the jobs. We don't care about shared state. This is actually written in Scala. You may have heard of Scarling or Starling. Those are earlier versions of this, which we wrote respectively in Scala and Ruby. So we wrote this, in Ruby and Scala. And then we wrote this so we could get more performance out of our queues and to make more of the requests on the site asynchronous. The current problem with Mongrel is that Mongrel you run multiple Mongrels on a single host. It's not like Apache, it's not multi-threaded. There's Mod Passenger out there. We haven't really started experimenting with that because we mainly run on Mongrel and it's what we know. Mod Passenger might be in the future. That gives you a little bit of multi-threaded support with Ruby. But in any case, incoming traffic and outgoing traffic is going to consume a mongrel. The more mongrels that are in use, the less traffic we can process, the more jobs stack up waiting to be processed. So if you're spending time during the lifetime of a request processing data, you're doing email, you're doing anything that could be handled offline, just don't do that. Move things to daemons. Don't make services dependent. When you make services dependent and you put work in the request cycle, you slow the user down. And your job is to get a request out to the user as fast as humanly possible. This includes anything, third-party services, URL shortening, any type of complex object generation, put it in a daemon. At Twitter, we have many, many different types of daemons. We have daemons that process SMS. We have daemons that process API requests. Our early Kestrel had problems with large numbers of jobs, but we fixed that. You have to be careful when you're doing this sort of asynchronous processing that the number of daemons are sized correctly for the workload. And one thing that we found really helpful was we had this seppuku patch, so the daemon would actually kill itself off after a certain number of requests to free up memory. Long-running daemons are really bad. They eat memory like crazy. Let's see. So MySQL, a lot of replication delay issues there. MySQL's replication is single-threaded. It's very slow. I've already kind of covered the social networking problem there. Sharding is important if you haven't done that yet. Let's see. Just want to skip ahead here. Okay. So you may have seen an inconsistent timeline sometimes at Twitter. And that usually happens because one of our databases goes out of sync, and we're bouncing you to a different service every time. We want to avoid that by using the write-through caching and by not having a database lock. So for us, the way that we're getting around that problem currently is by using functional write partitioning and functional repartitioning. We want to make sure that no one ever writes to our master write database because it slows everything down. We monitor the database constantly, And we attempt to find all the slow queries we can by either looking at the MySQL slow query log or by using mkill. Now, what mkill does is mkill is a script that will actually cycle through the database process table. And when it sees an incredibly long-running query, it will kill it. Now, you might think this is a bad thing because if you're mid-select, maybe you're trying to assemble your friends list or something, and the database connection falls out from underneath you, like, oh, I really wanted to get my stuff, but I can't because the database connection went away. In this case, the user experience is a whale. It's kind of okay because the user gets a whale, but that 3-hour-long query that someone accidentally kicked off, he's dead, and that request pipeline is opened up again. We don't want this to happen, but it's a good defense against runaway queries for the time being. What else? We try to maintain status.twitter.com. We have rare problems. We want to keep users in the loop, and you should too. If you don't have a status blog yet, get one and host it somewhere else. We host it on Tumblr. Put it on a different site. You might lose your whole network someday, and people would come to you asking, what's going on with Twitter? What's going on with your site? No matter how little information you have, keep the users in the loop. It'll stop the generation of press. It'll stop speculation and armchair engineering, which we've definitely been a victim of. And it'll keep your users informed. Okay, key points. Database not the best place to store things. Instrument everything. Use metrics. Don't make services dependent, and process asynchronously whenever you can. I want to thank everyone for letting me come here to Velocity. It's been a great experience.